Hey, what's up? Today is gonna be a bit more fun. I'm gonna start with a calculus review. First, I might just go through some things that I think I might like want to review. Maybe some questions of mine. I hope it's not illegal, but yeah, let's go. All right, I'm gonna do this later. Hold on. Okay. All right. Let's go through this. Let me just put it like right here. See if I can do this. Uh, all right. Let's. I guess let's just go through this. All right. Okay, so average temperature distance, you know, it is not the integral of the derivative, rather it is just straight up the original function. Um, okay, so this basically means like a average distance. For instance, if you have x as your distance, xb minus xa, and yeah, xb minus xa is the distance you have traveled. And let's see, what does this mean? I don't know. Wait, this is confusing. Let's just. Mm, I don't know. I don't know what it is talking about. All right. Next one. This is. I think this is the average velocity formula. Maybe I was talking about this, but yeah. If you have f and you measure the total, like the total. For instance, if f is velocity, the integral from a to b of f gives you the distance, or gives you the displacement, and the displacement divided by the integral, which is here. Just want to think that, how much has f been traveling, per unit time, I think. Because you're calculating the total distance f, or this object has traveled from time a to time b. And then if you take that range and divide the total displacement traveled in that time, you get like average displacement of like the unit time. So yeah, okay, that was something that I felt like I needed to review so that I won't be too stressed out on maybe the first question on my free response question. All right. This, yeah, some you just have to remember this. It shocked me when I was asked to do this in class the other day because it has been too long that I've done anything like this. The derivative of an inverse function is something that you should practice a lot before you go to the real exam. I haven't gotten anything right. I haven't gotten anything wrong that's like related to this because I have practiced in light of my pop quizzes that really just alerted me to remember the derivative of an inverse function. So yeah, the derivative of an inverse function equals the derivative of the what did I do? Oh, the derivative of a function, and then inside of the derivative of the function is the inverse of that function. Yeah, you just want to practice this formula a lot. Also, something else that you should practice is okay. I hope I can just go to somewhere that won't show you anything. Okay, let's see. Okay, let me just do this. Bro. So, okay, this is just a scrap piece of paper. Then let me show you something. So, how do you like know how to solve? Okay, if you don't, first, if you gotta remember what is the derivative of inverse of sine. If you don't, you can always like prove it on your own. So let's see. Um, say if you want to prove what is like the inverse of this thing over here? What is it? So um, first, I can't think of what it is right now. I gotta like practice. I gotta like remember how to. I know I gotta remember. I need to practice how to remember it. But we can always do this. Just prove it right there. So if you put sine, so this thing equals y, right? If you put sine on both sides, this thing cancels out, leaves out x equals sine y. And then if you take the derivative of these two things, you get 1 equals cosine y dy dx, because this is like I don't know how to call it. You just have to do it. It's like different. It's like implicit differentiation, implicit differentiation. And then dy dx now equals 1 over cosine. Cosine y. This works because you have once already set up, you know, the function as sine inverse sine equals y, and then dy dx yields the derivative of sine inverse sine x. So yeah, I hope that makes sense to you right now. And what is cosine y? So cosine y, as we know, cosine squared plus sine squared equals 1, and this gives you cosine y equals 1 minus sine squared y in the root, and then dy dx hence equals 1 over root 1 minus sine squared y. And what is sine squared y? Sine squared y basically is x squared. Sorry, x squared. So you get 1 over root 1 minus x squared. Because, okay, look, if you square this thing will become squared. Since you have already canceled these, you get like x squared equals sine y squared. I hope that makes sense to you. So that's how I get like 1 over root 1 minus x squared. And for cosine, it works the same, but you just have to prove it. And as far as I know, the inverse of tangent x is the only thing that you really want to remember. Let's see. So inverse of tangent x, you can either like do both of the inverse for these. I think you can do it, but actually no. Dude, please remember this. This is very easy. It's just 1 plus x squared. This is the inverse of tangent x. Okay, let me see if this content is right. Inverse of tan x. So the inverse of what am I talking about? It's the derivative of arctan x. What have I been talking about? Okay, ignore all of that. I was talking about the derivative of inverse of tan x. I didn't know where I got wrong. All right, just know that I've been just talking about this. So as you see, let's wait. Why are these so confusing? What are these doing? So okay, 1 over 1 plus x squared. All right, as you can see. All right, next thing. Let's go. Okay, this was a confusing. This was something that I had to like take note of. Let's see. Because the smallest possible increase rate. Oh, you just want to know how to like explain. You want to know how to explain for 0. So is there a time t at which gt is increasing at a rate of 0.2 gallons? Oh, this is easy because this is the MVT, mean value theorem. Let's review about mean value theorem. All right. So, man, I should have something to like do scrap with. Let's see. Okay. Ignore my things on freeform, right? Or ignore these. All right. Let's go. So what was I talking about? Oh, MVT. What is the MVT? So the mean value theorem states that in like A, B, close parentheses, actually, because like for A, B, open parentheses, it has to be continuous, and close parentheses, it has to be differentiable, like the function fx. All right. And also MVT says that if it satisfies all of these, then at some point the derivative at this point must equal to like fb minus what am I writing? It must be fb minus fa over b minus a. This is basically a representation of the average rate of change, a rock, because So for instance, you're measuring this. You're measuring the change from here to here. So this is like FB minus FA. This distance right here, right? This distance right here. And then the whole interval is like B minus A. So when you do this, you just measure the average rate of change of each unit in the range, how it changes. So let's say, oh, this thing will be this. The value the value it yields is basically this. This is the slope, and there has to be a point in this case. It might be here or here, that FC equals this thing, the A rock. All right. Yeah, just think about it, because there has to be a point where it goes from decreasing to increasing, and then some point the derivative has to be that, if it is continuous and differentiable. Yeah, this is really very important for your second question on your FRQ. It will ask you either it's like MVT or IVT, or something like that. The IVT is basically like, there has to be a value. If it is continuous, there has to be a value that is between like FB, FA. There has to be a value that is like smaller than this, bigger than this. So X. Okay, look at it sideways. This is a smaller equal to sign. Smaller equal to sign. All right. It's not a VI. It's not a VI. It's a smaller equal to sign. But yeah, here, look, there has to be a point C. Maybe it's here. It's here. So that's the MVT, and it's really important to remember that. I forgot about it when I was doing this, so that's why I said how to explain. Yeah, you just want to explain it like that. You want to use MVT because of the MVT rule, which states that this and this, it proves that and that. Okay. Okay, next. Oh, you just want to remember these, I guess. So don't be confused when you see something like this, like related to limits. I hate limits because it's too much writing. Why do you have to write LIMH arrow 0 every time? Now this is like very confusing, and these two are too similar, bro. They're like identical twins. Look, H is basically a very small like difference from the value that you're trying to take the derivative of, and this is basically like when x equals a, like what is the rate of change. So there's the H rule. I don't even know how to explain it. It's just remember, these are like just taking the derivative. You know how to take the derivative now. You know how to take the derivative now, sorry. Just use the number rule. And yeah, when you look at these, they are basically asking you for the derivative. And also, if you are asked, I don't know if you will be ever asked to represent anything in a limit notation, but if you were, just remember these two. And low p dot is very important because on some pre-response questions, especially on the non-calculator part, there will definitely be a question that asks you about something like this. This is when when the limit doesn't work. For instance, like if gx is like a constant value, it gives you 0, right? If it is 0, it's indefinite, or it gives you infinite. It's just, it shouldn't be the answer, right? If you're having like a 0 on the denominator, it will not be a correct answer. And also, I think for infinity, even if the infinity is in the yeah, I mean, I think it can be like a answer for if it is at the numerator. I mean the infinity, because when a limit approaches something, it can be infinity. However, okay, but there are somewhere you can find like a limit to this, because yeah, it has to make sense, right? The answer has to make sense. So take the derivative of the top and bottom. This gives you the same as like the limit of these of the original function, the derivative over the other derivative, and then yeah, remember how to do this, and yeah, that will give you a reasonable answer. Okay, and then next one is yeah, I thought this was helpful because if you know how to if you know how to like manipulate the limits, you can do more things easily. So for instance, if you have these, it's limit of plus limit g. I don't know if you ever have to use them, but there are some questions that require them, I think. And yeah, it's pretty good. Just remember these. You know, you can split them. These are almost like integrals, honestly, or like just parentheses. And it's really just it's amazing when you wonder about math. Like there are a ton of notations, but you can also like play with them. All right, next one is like next one for optimization problems. I don't think you'll ever see optimization problems nowadays, but if you have anything, you want to represent, like for instance, if this is the hypotenuse equals y squared plus x squared. If you have a point, for instance, if you have a point that is changing right here, and it might be a point on a circle, right? This point is constantly changing, so sometimes it might be here, which this will give you a new triangle, right? But yeah, okay, if you have a point, this is the x, this is the y, and then you might be asked to change the rate of change of z, which is the hypotenuse. You got this z and you got this z. So how do you know how it changes? So you want to use the implicit differentiation on this. It will definitely be like something according to time. For instance, dz dt. How do you find dz dt? Z dz dt equals dy dt, y dy dt plus x dx dt. The reason is that z squared equals y squared plus x squared. This is like for like always. It will be like this all the time because it's just a triangle. You want to find like a relationship between them. For instance, this is still x, this is y. So yeah, then this is z. And yeah, if you simplify, it's 2z dz dt, and then yeah, you know the deal. And then you want to divide it by 2, and you get this thing, and then you can measure the rate of change and stuff. So yeah, it's not that hard. Like, you just want to remember that any form of something over dt is just measuring the rate of just measuring the change compared to another value. In this case, it's like anything like z, x, y compared to time. All right, calculus is fun, low key. Okay, I don't think I have any more. Okay, I'll talk about for optimize. Oh, I'm done with this. All right, so that's video 1, or I'll just call it a day for day 6, and then day 7's video will be me doing an FRQ. I'll see you there.